Okay, good morning, everyone. I want to welcome you to another multivariate statistics class. Of course, today we're going to be focusing on multivariate linear regression. I remember earlier in the week, I actually, um, how I walk you through uh, multivariate linear regression, the one with one response variable. But right now, we actually want to talk about the one with multiple response variable. So, having gone through the univariate one, I mean, the one with a simple response variable, of course, we're actually going to move fast today because we'll be able to, all we just need is to generalize or extend the univariate version into a multivariate version. So everything is going to start with a model when we're trying to look into relationship. If you look at the specification of this model, you're going to notice K, okay? So that very K, is actually referring to a particular response variable, okay? So of course, the K here, you're actually going to see from 1 to n. So 1 to n means the numbers of response variable that we're going to have is m. That's what I mean. So all of this, represents, the description of each term in the model. And of course, you can see our error follow a IID, normal distribution with you can see the zero here because subscript M indicates that we're actually going to have zero for each response. Okay, that's what it means. Okay, because the number of response that you're going to have, you're also going to have the corresponding numbers of errors associated with that. And of course, this is our variance or covariance matrix. Now, can we also, so the question is, why do we call it multivariate? It is actually called multivariate because the number of response variable is more than one. If the number of response variable is one, okay, and you have multiple explanatory variables, that will be called simple linear multivariate. You know, let me just say this. Let's say, for instance, you have m equal to 1. M equal to 1 means the number of response equal to 1. If the number of response equal to 1 and the number of explanatory variable is 1, then you have simple linear regression. But situation whereby the number of explanatory variable is more than 1 and you still have one response, that is a multiple linear regression. We can also have situation whereby the number of response variable is more than 1 and you have one explanatory variable. That will be multivariate simple linear regression. But situation where the number of response variable is more than 1 and the number of explanatory variable is also more than 1, then you have multivariate multiple linear regression. Okay, now just like what we did in in a single response situation where we're specifying the model, we stated assumptions. We're also going to have assumptions for multivariate linear regression. So these are the assumptions. Relationship has to exist between the set of explanatory variables and each response. That's why you see YK, particular response. Okay, and of course, you know, SIK, SIJ and YIK have to be observed, random variables. And of course, I wanted to pay attention to the error here. If you take a look at the first one here, it's a vector on its own. That would be the error associated with response y with respect with the first response. Okay, don't forget we have m number of response, right? Variable. Okay, so we're also going to have error associated with all of that. And of course, that is the distribution. Okay, and of course, the if you take a look at this is for a particular this guy here. If I have a BK, okay, this is for a particular parameter. Okay, for particular response. If response variable for a particular response, you're going to have intercepts and on slopes. Okay, so which means for k start from 1 to m, which means you have m number of responses. Okay, you're going to have set of days. So I just wanted to understand that. Now, how is the conditional distribution of y given s going to look like? Don't forget, uh, the conditional distribution of y given s follow normal distribution. And of course, the mean is this guy. The mean is a model, okay? And the variance is sigma kk. Whenever you see me using sigma kk, that's a variance. If I just write sigma k, that's a standard deviation. Does that make sense? So sigma kk means sigma square k. Okay, and of course, we expect a constant variance for each response, which we call homoscedasticity. Okay, the homogeneity of variance for each response. Now, how do we write in matrix form? I need you to pay attention to what I want to start, so what I want to review right now. Okay, so how do we actually, uh, present this in a matrix form? Because when you're working with multivariate data set, it's actually going to be very easy to navigate if you go by way of a matrix. Now, this is a matrix specification. When you take a look at this, why? If you look at the what I used the other time for situation, uh, where where we have a single response, I think I use this. Can you see that? That's a specification for single response. But for multiple response, you see what I'm having? That very Y here is a vector. That very Y is actually going to have first response, second response, and each response, they're actually going to be collected over observations. Okay? Now, if I want to see, uh, this is the definition. Please pay attention when you specify a module like this. You need to be able to tell us what Y, what S, what B, what E represent. As you can see here, there's something I need you to, there's something that is not going to change. This guy is not going to change for both single response and multiple response. But the only thing that is going to change, I'm gonna tell you what is going to change. This guy is going to change because you now have Y1 to YM, M number of responses. B is going to change. Okay. You have a B1 up to Bm. The B1 here will mean you're actually going to have regression parameter for Y1 for the first response. You're also going to have regression parameter for the second response and so on like that. Okay, so this is a particular set of parameters. And of course, E also going to change. Of course, all the time, the dimension of Y always going to be equal to the dimension of the error. Okay. So, you know, if this one is m by m, that also is going to be the same. They're also going to have the same dimension. Okay. Now I'm going to show you how you can write the matrix down. Okay. Please, I need you to pay attention now. Okay. So pay attention to this. Now look at my y here. This is for single response collected over so many observations, n observations. Okay, we're going to have y. We're going to have the second one. We're going to have the up to the. This is the m1. This guy, like I said, doesn't change. It remain the same. But you know what is going to change? Please pay attention. I need you to see here. This guy will be the set of parameters for this guy. Okay, this guy up to the m1, that will be the set of parameter for this guy. Now, the dimension of y should be the dimension of error. Okay, if I have this one, if this is the actual response for the for the first response, I can have a predicted response for that. And the moment I have a predicted response for that, then I will be able to calculate my error. Because the error is going to be the difference between the actual response and the predicted response. Okay, I'm going to do that all the way over the number of response variable. Can you see that? Is there anyone who doesn't understand this specification? So what if I ask you to give that specification in exam? Okay, so take a look at that. Before you can begin any analysis in statistical framework, we actually need to specify our model. Okay, now I actually want to move right now. Let's come to the assumptions. Here, there's going to be a lot of assumptions. We're actually going to have assumptions on the errors. We're going to have assumptions on the vector of errors. Vectors of errors. Don't forget. Why do we have vectors of errors? Because we have error associated with the first response, error associated with the second response, and so on like that. We're also going to have assumption associated with the vector of the transpose of the error. Now, if you take a look at what I'm having now, this particular guy is talking about when I take error that has to do with a particular response. Okay, that error follow normal distribution. Okay, now if I want to talk about error in general, okay, for the row, this is for the row, this is for the column. What am I talking about? I'm gonna go back. Okay, you know, when you take a look at what I have here, we have the one for the column, we also have the one for the row. Okay, can you see that? You want to look at it from the row. Okay, if you want to look at it from here, that would give you the error of observations for a particular response. But what if you go this way? If you go this way, then you are referring to the error associated with a particular observation across all responses. Does that make sense? So the error here, we have it in two ways, in the column way, in the row way. And of course, we need to be able to impose assumptions on that. So this is the assumptions here. Take a look at that. This is the assumptions. Now we're also going to have assumptions of the vectors of the error. Okay. Now, please pay attention to these two. You remember the other time that we talked about chronicle products. The idea of a chronicle product will actually be applied. If I were you, you need to be able to go back and revise all your knowledge on what we've done before under the matrix algebra, okay, particularly the chronicle products. We're talking about chronicle product, okay? So whenever we want to have something to do with, you know, the vec of E, and where E here, of course, has errors associated with the multiple response. I needed to take a look at my E. Okay, you know, if you take a look at this, my E right now, this particular guy, okay, is actually talking about, you know, error associated with multiple response variables, and because of that, if I want to talk about the distribution of an uppercase E, I'm going to be talking about vector E. Okay, that's what you see here, the vector E. Okay, the vector E follow normal distribution with the mean of this. Don't forget, the dimension of the error the other time, you know, if I go back, the dimension of the vector E is n by m. Do you see that? That's n by m. Okay, And that was why you actually seeing this guy here. Take a look at this. Okay, you follow normal distribution with the zero, and that very zeros, the dimension is going to be n by n, and of course, we also going to have the the variance. The variance is going to be a chronicle product between the covariance and identity matrix of order n. Please pay attention to that. Now, that's a chronicle. So if I have this, of course, I can do the vector for the transpose. In the vector for the transpose, oh my God, what I'm just changing, take a look at that. I'm just changing position. Okay? I'm only changing position for the variance. If you take a look at that now, that is that. Now, the next is you remember under a single response. Remember we talk about distribution of y given s, right? Y given s, it follow normal distribution. The mean is going to be the module, okay? And the variance is going to be sigma squared. But in the case of a multiple response variable, okay, we're going to have a vector y given s. We're also going to have a vector y transpose given s. Don't forget, when we're dealing with the vector of the error, we said the vector of the error. We also talk about the vector of the transpose of the error. We're also going to be doing the same. Okay, take a look at that. The vector of y given s. Okay, so what I'm trying to tell you here is that this is the mean. Okay, this is the mean of this guy. Then this is the variance. Okay, so you can see the mean, you can see the variance. In the case of a single vector, the variance was a sigma square identity. But right now, it is a chronicle product between the covariance and their identity. Take a look at that. Okay, so the moment I understand the distribution of the vector y given s, of course, I can apply the distribution of the vector transpose given s. So take a look at that. Okay, and of course, um, you need to be able to understand this. The vector xb, okay, the vector xb is the same as this. Is this, don't forget, it's the same thing as, vector x. The b is going to come out. That's why we have a b transpose of that. And of course, we can also talk about the vector of the transpose. Okay, so that is what you're seeing. So these are kind of assumptions that you need to be able to understand. Now, this is trying to define the vector product of b transpose s transpose. Okay, which is what we have here, and of course defined as that. Okay, and of course we can also talk about the vector of y transpose. The vector of y transpose is defined as that. Don't forget the diagonal. This guy itself, this guy is going to be the covariance structure for y1. Okay, this is going to be a covariance structure for y2. It's going to be a covariance structure for ym. We actually believing that they have equal covariance structure. So take a look at that. Okay. Now, I actually want to move right now. If there's any question, to make sure you stop me. Now, if I'm working with a multivariate linear regression, and I also need to have a way to estimate the parameters, there's going to be a lot of parameters. Parameter, the intercept and the slope for the first response variable, for the second response variable, and that was why you actually seeing here, you're seeing k. Can you see? Can you see here? You can see you're seeing k. That will be for a particular response variable. There's going to be a lot of response variable up to n. So we actually want to estimate the parameters using the method of ordinary least square. The method of ordinary least square will enable us to have a drastic reduction in the sum of square error. Okay, we actually want to estimate our parameter in such a way that we minimize the sum of square error. Okay, in matrix form, this is it. Now, what I'm going to do, actually, if you take a look at what I have, of course, I'm going to differentiate with the respect to B. Okay, so when you take a look at what I have now, okay, another way I can rewrite this guy, if you expand this, okay, of course, this guy can be written as y minus xb, okay, uh, transpose, okay, multiplied by y minus xb, okay. So when you expand that, you're actually going to have this guy, okay. Then you differentiate with respect to b, okay. This is what you're going to have. This is what you call normal equation. Then you're going to set that to 0, okay. You're going to set all of that to 0, okay. When you set to 0, then you're going to solve for b. When you do that, finally, you're actually going to have this guy. So this is the OLS solution, okay. And of course, for a particular response variable is this guy. Okay, this is for a particular response variable. This is for all of them. Okay. Now, the next thing now we want to talk about the fitted values and the residual. Okay. Don't forget, if I have my module specified, okay, and if after parameter estimation, if I know the values of the parameter in my model, then I will be able to have it fitted. Okay, this is a fitted. A fitted is going to have a cap. This is for a particular response variable. Okay, for a particular, for Kate response variable, a particular response variable is going to have its intercept. It's going to have its slope as well. Okay, this is in matrix form. Can you see that? That it is in matrix form. Okay, and then of course the moment we have predicted values are called fitted values. The moment I have fitted values and I have the actual y, then I can compute the error, because the error is going to be the difference between the actual response and the predicted, which is exactly what you're saying here. Take a look at that. That's what you're saying here. That's a gap. Error is a gap. Okay, a gap. The residual, is a gap between. Or some of you may be wondering, what is the difference between error and residual? Okay, when you an estimated error is called residual. An estimated error is called residual. You can see here we are estimating error. That's a residual. This is a particular response, and this is in matrix form. Okay, is there anyone who doesn't understand that, or doesn't understand this? Provision? Anyone? All good, right? Okay, now I'm going to move right now. Now, I actually want to move to art matrix. We talk about art matrix in where we were dealing with a single response. We're also going to talk about art matrix here. Okay, so what do you see that I'm actually plugging in? If the fitted model equal to that, and I know that my B cap is this guy, right? Then I'm going to have all of these. And if I have that, okay, anything other than y, this guy here is an art matrix H. So the benefit of the art matrix in multivariate analysis is and in general is to enable us to transform the actual response y into predicted. Okay, okay. Of course, it also has some other benefits in detecting outlier and high leverage. Okay, now that's an art matrix. Okay, now if you investigate this guy, because moving forward to conduct statistical inference, whether we want to conduct inference about what is it called, predicted values, or we want to conduct inference about um, maybe the average and so on like that, we expect the art matrix to be symmetric and to also be idempotent. So idempotent means if I use this guy to multiply itself, it must give itself. You can try it out. They're symmetric. When I find the transpose of this guy, it should give me this guy. Okay, the transpose of H. So by symmetric, the transpose of H should be equal to H. That is what we mean by symmetric. Okay, but by idempotent, when I multiply at matrix by itself, it should give itself. Does that make sense? So you can investigate that because that is very, very crucial moving forward. Now, how do we do multivariate regression in R? Okay, we still want to use the data set. This data set is our input. Okay, this is my data frame. Okay, but right now, uh, let's look at the response. How many response do we have? Oh my God, look at my response Y. My response Y, we got 4: MPG, DISP, HP, and WT. Okay, so those are my response Y. Okay, my response Y is more than one. And that's why I want to do multivariate linear regression. And these are my explanatory variables. Cylinder AM and CARB are my explanatory variables. Now, do you see the coding? Okay, you can see I declare my response variable and I declare my explanatory variable. Now, if I want to perform a multiple, if I want to, perform a multivariate, multiple linear regression in R, can you see the code? That my Y, that my Y here is actually this guy. Okay, for response variable. And you know what? Oh my God, look at the results. I'm actually going to have result for each response variable. Okay, for each response variable. Can you see that? For each response variable, I'm actually going to have the intercept. I'm also going to have the slope for each response variable. Is there anyone who doesn't understand that result? Is there anyone who doesn't understand that result? Ask question. If you don't understand, okay. If you don't understand, make sure you ask question. Okay, now that is parameter estimation in R. Okay, working with a multivariate or multiple linear regression. Now, we also want to talk about, you remember we talked about decomposing the total sources of variation into various components when we were dealing with single response. We're also going to do the same in the multiple response. So, but the name we call that is actually, we call that sum of square and cross products. Okay, so for the total, this is that. For the total, okay, don't forget this total involve so many response variable. Okay, the total is a total variation. This is the explained variation is the sum of square regression. And this guy here is the unexplained. Okay, our model does not have ability to explain everything. There's always going to be something left unexplained. Don't forget, if you have set of response variable, you're also going to have set of predicted response. Of course, you're going to have opportunity to have a predicted response after you've been able to have your parameter estimated. And of course, these are corresponding degree of freedom, okay, for each error, variation component, okay. Now, this is in the multivariate form. Take a look at that. I'm actually going to move, okay. And of course, this is the partitioning. Okay, this is actually showing us how the partitioning of the total sources of variation within a multivariate setting is going to be done mathematically. Okay, and at the end of the day, we end up into explained variation and the unexplained variation. Okay, so if I were you, you can follow that. Okay, now I'm actually gonna move right now. Okay, how do you actually compute the sum of squared, okay, and cross products in R? Okay, maybe you want to have a way to compute what is the amount of explanation the module able to do, and the one for the error. Okay, so when you take a look at the code here, okay, actually represent, the sum of square, the SSPT. Don't forget the SS. That is the total sources of variation. Okay, I'm talking about this guy here. Okay, so how do we do that now? And when you are doing that in R, of course, these are the code, and whichever way you want to go, okay, whichever way you want to go, okay, you're still going to get the same results, okay. But you know what? When you're doing it, you're actually going to have for each response variable, because don't forget, if I want to talk about the sum of square total, sum of square total is total variation. Total variation has to do with the response only. I'm going to say that again. The total variation, you are talking about variation around only response variable, not predictor. And that's why we're only focusing on the MPG, the DISP, the HP, and the WT. Okay? So take a look at that. Now, we want to move right now. Now, we also want to have a way to estimate our parameters in the multivariate linear regression using the method of maximum likelihood. You remember we did the same for a single response. Okay, and how do we, and today I've showed you how you can use the method of ordinary least squared. The method of ordinary least squared put into consideration minimizing the sum of square error. Okay, minimizing sum of square error, in order to obtain, to obtain optimally the estimate of parameters. But the method of maximum likelihood, on the other hand, rely on assumptions of normality. Okay, so you need to be able to write the multivariate normality. Okay, assuming the model. This is a multivariate normality assuming the model. Then you're going to find the likelihood of that. This is already in a likelihood form. Then you're going to take the log of the likelihood, because if I want to optimize likelihood, it's going to be complicated because it's multiplicative. And of course, if I introduce the log, okay, the logarithm to both sides, it's going to make it easy for differentiation. Okay, so differentiating that, okay, and set to 0. Of course, that's what I'm doing here. I'm differentiating with respect to b, then you set to 0. At the end of the day, you're also going to have this. Of course, you can see for OLS, we also derive this. For maximum likelihood, we also derive this. So the OLS and the maximum likelihood technique will give you the same expression. Is there any question on this? Okay. Now, because of my time, I actually want to move. Okay. Right now, how do you remember when we're dealing with a single response, I show you the estimate of the error variance. But right now, in the multivariate, we're going to call it the estimate of the covariance. You know why? Estimate of covariance, because there's more than one response variable is involved, and there's possibility they may be having correlation. Does that make sense? So right now, this is the estimate of the error variance, okay? And the estimate of the error variance is just going to be the sum of square cross product for the error, okay? Which is the unexplained divided by the degree of freedom, okay? This is in writing it in art matrix form. And this has been shown to be unbiased, okay? Unbiased in the sense that we assume, we derive that the expectation of the estimator, the one with the cap, is the equal to the true covariance structure. So that is unbiased. Okay. Then you remember that I also walk you through the maximum likelihood estimate of the error variance for single response. We're also going to have it for multiple response variable, but in that one, it is biased. Look at that. Because the expectation of the maximum likelihood estimate is not going to be equal to the true value of parameter. Okay, but if I actually want to figure out the bias here, if I want to figure out the bias, so the bias of an estimator is equal to the expectation of the estimator minus the population parameter. Okay, so, and this guy, okay, is this guy here, this expression. So if you do that expression minus the true covariance, you know what you're going to have. I'm going to show you what you're going to have. What you're going to have is this guy here. Let me clean up so that you can see. So that is what I'm doing here. Can you see what I'm doing here? Can you see what I'm doing here? Okay, I'm trying to find the bias. So this guy will give me the bias of an estimator. So the bias of an estimator, okay, is the expectation of the estimator, okay, expectation of the estimator minus the true covariance. At the end of the day, this is the bias right now. That is the bias. Okay, and you know what? Asymptotically, if I take the limit, or as n tends to infinity, maybe I have a sufficient large sample size, then this is going to tend to 1. And if this guy tends to 1, then you're actually going to see that the bias is going to be 0. This is what I'm trying to say. When n tends to infinity, sorry, this guy tends to 0. Okay, when n tends to infinity, because the denominator is going to be infinity. Anything divided by infinity is going to be 0. If 0 times that, then the bias should be 0. When the bias of an estimator is 0, then that estimator will be unbiased. And that is why we call this asymptotically unbiased. When sample size is large, it will be unbiased. Okay? That's exactly what we mean. Now, I want to move right now. Okay? I want to move right now. Now, just like what we did under the single response, we can also compare uh, the uh, the maximum likelihood variance with the estimated variance. Okay, now these are the two expressions. Oh my God. The one divided by n is the maximum likelihood variance. The one divided by n minus p minus 1 is going to be the estimated error variance. And of course, just like what we did the other time, we expect the one from the maximum likelihood to be smaller. Okay? The one from the maximum likelihood to be smaller. Okay, now how do we do that now? Is there a way I can estimate my error covariance in R? Okay, this is the estimation. So what I'm trying to show you now is how do you estimate both? Okay, you want to estimate the error covariance in R. I put the code here. Okay, can you see the code? And let's see the result. Oh my God. If you take a look at this guy and this guy, you're actually going to see here, compare this guy with this guy. You can see here, this guy is smaller than that guy. Can you see? Okay. So the maximum likelihood one is going to be smaller. That's exactly what I mean. Now, actually, want to move right now. Now, the same way that um, the beta cap is going to vary under single response. It's also going to vary under multiple response. So we need to find the average. This is finding the average. What is the expected value of a B cap? If you follow what we've done before, okay, you're actually going to see it's also going to be unbiased. Don't forget the expectation of Y is XB. And when you take a look at that, you're actually going to see that this is going to be identity B and it's going to be B. So what does that mean? It means B is the mean of the B cap. And another implication here is that B cap is an unbiased estimator. Okay, now that we have the mean, we can also have the variance. Okay, now when you want to talk about the variance, we talk about the variance of the vector B. Okay, we talk about the variance of the vector B transpose. We also talk about variance of vector B. Okay, take a look at that. Now, please, I need you to pay attention. Okay, this is a derivation. You remember the other time when I was walking you through single response, the variance of Y. Let me remind you. For single response, the variance of a B cap for single response, the variance of a B cap is sigma squared, okay, x prime x inverse, okay, for single response. But for multiple response, we're going to talk about vector B prime instead of just B transpose. B hat. Okay, instead of B hat, we're going to talk about vec of that. Okay, so vec of that. Okay, so wait, take a look at what I'm doing here. Okay, now let me tell you something. What is your B? B is X transpose X inverse X prime Y. Okay, then what would be the B uh, prime transpose? Okay, the B transpose is this guy here. Can you see that guy? That is the transpose of this guy. You know what I'm gonna do because of my time, and I also have a doctor's appointment. Um, I'm gonna stop here, and I'm gonna make recording of the remaining parts, join them together, then share with you. Okay? So that's what I'm gonna do. So I'm stopping here, because I want us to finish this material today, so that we can start a new one tomorrow. But I'm gonna make a recording of the remaining one. Okay? I stop here. I'm gonna make a recording of all of that. Okay? So that's what I'm going to do. Okay? Yep. I want to quickly get to my appointment. So see you tomorrow.